All right, welcome back everyone from our short break. Hope you guys had some time to stretch, drink some water before our next incredible speaker, Xinyun Chen.
Xinyun Chen is a PhD candidate at UC Berkeley. Her research lies at the intersection of deep learning, programming languages, and security. The former research intern at Google Brain and Facebook's AI Research Fair currently focuses on neural program synthesis and adversarial machine learning. Please give her a warm welcome.
Thank you for the introduction. So you can see my screens in the presentation mode, right?
Yes.
Okay, great. So hello, everyone. My name is Xinyun Chen. So it is my great honor to share my research with all of you here. So during my PhD research, my main focus is on developing deep learning techniques to automatically write programs for us. And this is what we call program synthesis. So why do I want to study program synthesis in the first place? The reason could be pretty simple. Nowadays, programming has been everywhere, but programmers are not. And even for expert programmers who mostly pretty enjoy coding, they may still get tired and unhappy after doing a lot of tedious or error-prone implementation. It is extremely painful when there are some bugs that are hard to find manually. Therefore, it would be great if there is a machine that can happily do the work for us. Note that program synthesis is not only for programmers. Numerous real-world applications intrinsically rely on program synthesis, and they could affect millions of end users. One of the earliest practical program synthesis applications is the flash fill system for Microsoft Excel. We are given a few lines of data cells as the context. The flash fill system automatically synthesizes a program for string transformation so that it could auto-complete the spreadsheet data. Meanwhile, semantic parsing is an important component to develop natural language interfaces for many services, including workflow automation and virtual assistants, where we want to synthesize a program from a natural language sentence or dialogue. Before all the advancements of deep learning, program synthesis is already a long-standing challenge for artificial intelligence, programming languages, and software engineering communities. Classic symbolic program synthesis approaches are largely based on heuristic guided search, and they are pretty powerful when the program specifications could be formally defined. On the other hand, rule-based approaches have also been designed for a number of program synthesis applications. For example, some grammar-based tools have been developed to migrate code in a source programming language to another programming language. For code optimization, many compilers have integrated rules to transform a program into another semantically equivalent and optimized program. Although symbolic program synthesis methods have been used for many years, there are some clear limitations regarding their applicability and scalability. First, all these existing symbolic program synthesis frameworks require heavy manual work to design both the search heuristics and the rule set. These design choices are often problem-dependent, which means that a slight change of a task may force the developers to start all the manual work from scratch. More importantly, the formats of specifications supported by these approaches are limited. For example, they could not easily support complex specifications such as images and natural language descriptions. These limitations kind of motivate the recent research on deep learning for program synthesis or neural program synthesis. So this is a pretty new area and that it just emerged a few years ago. And I've been working on this direction since the very early stage of this field. So nowadays we have witnessed the success of deep neural networks for many tasks, especially for image recognition, some standard natural language processing tasks, and a few competitive games. When a large amount of data is available, deep neural networks are able to learn good representations for diverse input formats. The most desirable property of deep learning techniques is that they could effectively feed the training data, which saves the manual effort in designing rules. So during my PhD, the theme of my research on neural program synthesis lies in two folds. The main goal of my research is to advance the field of deep learning for program synthesis so that we can improve the model performance. And I have been developed a neural program synthesis approaches that synthesize complex programs from diverse specifications. On the other hand, besides considering program synthesis as a task, I also think about program synthesis as a means to achieve generalization for a broad range of applications. And I have been working on bridging neural and symbolic techniques for better generalizability and data efficiency. So specifically, in terms of the applications, I've been working on neural program synthesis from various specification formats, including input-output examples, natural language descriptions, and reference programs for software engineering. In this talk, I will discuss 2 lines of my research. The first topic I will discuss is about a program synthesis from input-output examples, where we propose execution-guided neural program synthesis technique to improve the model performance. Another topic is to develop program synthesis techniques so that it could better understand the complex natural language. So let's get started with the first part. Before I go into our concrete task, here I want to start with a big picture about the progress of input-output program synthesis using deep learning. The earliest work in this domain focused on simple list manipulation, such as sorting and long-digit addition. So let's use this task as an illustrative example. As you can see, there are a few input-output pairs here, where each of the input and output is a list. So what should be the program mapping these inputs to the outputs? Sorting, right? Pretty simple in this case. So we call these input-output examples, which will be used as the input of our model to specify the functionality of the program. Then during the test time, we feed some herd-out samples that do not show up in the input-output examples so that we can see whether our generated program can generalize to different cases. And we consider the program to be correct when the outputs match the reference. Then you may argue that, well, learning a sorting or addition program is a good starting point for this line of research. But in practice, usually we do not really need to learn a model to generate these simple programs. Then I'm going to formally discuss the flash fill task that we mentioned before. So recall that in this task, we want to auto-complete the spreadsheet data. So basically here on the slides, I'm showing like 2 columns, column A and column B. Then each column has several rows. So basically we can treat all data in column A as the input, all data in column B as the output. We want to generate a program to transform from column A to column B. Then our input-output pair is the first row. We see that we want to transform the input Yoshua Benjo into a Y Benjo. So basically we want to abbreviate the first name of a person. Okay, then if we look at the program that actually generated by the flash fill system in Microsoft Excel, we can see that it is not in a full-fledged language like C or Python. So this is actually a domain-specific language designed by the flash fill group. This is trying to do some regular expression-based string transformation. And I won't go into the details of the syntax of this language, but as you can see from this program, their current domain-specific language mostly just handles short sequential programs, so similar as prior work. And this is reasonable for their applications because for a string transformation on user-written spreadsheets, most programs themselves do not need to be very complicated. And the main difficulty comes from how to infer the program correctly, given only a few input pairs. Then in recent years, there is a new benchmark called Carol. It is released by Microsoft. This domain is adapted from a Stanford CS introductory course, CS106A. And the general goal is to control a robot in a grid world so it can reach the target state. So from this sample program, you can see that a Carol language includes control flow constructs such as loops and conditionals, which makes this domain-specific language much more complex than prior languages studied in the domain of input-output program synthesis. So in our work published in ICAR 2019, which is a top-tier machine learning conference, we propose new techniques to handle such languages with richer semantics. And I will discuss this work now. Before we delve into our approach, let me introduce previous methods we compare with and see what are missing there. Suppose each program has k input-output pairs as the specification. So in general, we consider k to be small, like for our Carol task. k is equal to 5. Then in the model, there is an encoder to embed these input-output pairs. So which is the convolutional neural network in our case, because our Carol model inputs are like grid words. Another part of the model input is called P-1. So actually, this is the previous program token generated by the model. Then we feed both parts of the input to a decoder to generate the next program token. So here we use an LSTM as a decoder. And basically, this entire model will generate a program as a token sequence. So this framework looks pretty much like a direct adaptation of encoder-decoder architectures for other tasks like machine translation. So what are the issues here? We can kind of notice that during the program generation process, in this model, we always feed in the initial input-output pairs without leveraging the program execution. So let's look at a concrete example and see why this could be a problem. Suppose we want to synthesize a program to satisfy these two input-output pairs. This problem is relatively easy and can be solved by a sequential program, where the robot first puts a marker in the current cell it stays in, then moves towards its northwest direction. So at the first time step, the model should predict put marker, which puts a marker in the current cell. Then after this prediction, these grid words would become more similar to the target states. So somehow the program specification is supposed to be changing during the program generation process. However, the existing framework doesn't take such state transition into account and still feeds in the same input-output pairs throughout the time. In this way, the semantic meaning of the program is not effectively leveraged by the synthesizer. Therefore, we propose a technique called execution-guided neural program synthesis. The basic idea is to view the program as a sequence of manipulations to transform each input state into the final state. So these input and final states are specified by the input-output pairs. From this perspective, when a partial program is generated, we can immediately execute it and obtain the intermediate program states. So that the synthesis of the follow-up program statements can be conditioned on these intermediate program states. These intermediate states provide a more fine-grained specification. So let's take a look at the same examples as we shown in the previous slides. At the beginning, the current state is the initial input, and the target state is the output. So this time, after the model predicts the statement put marker, this statement is immediately executed and results in the new state. So that at the next time step, this new state is used as the input to the model and guides the subsequent synthesis of the program. So in this way, we show that our model can leverage intermediate execution results so that at least it could generate sequential programs more accurately. Then let's see how we can extend our framework to synthesize programs with branches. Every time when the model predicts an if condition, we know that this statement will have two branches, one for true and one for false. Previous work treats such programs in the same way as sequential programs, where all input-output pairs are fed into the model regardless of whether they satisfy the condition or not. However, intuitively, the synthesis of the true branch only depends on those input states that satisfy the condition, and the first branch depends on the rest of the inputs. Therefore, in our execution-guided synthesis framework, when an if condition is generated, the model first evaluates the condition and splits the examples into two sets, then synthesizes the true and the false branches using the corresponding subsets, and finally combines the two branches together. In this way, we make a better use of the program's semantic meaning to guide the synthesis process. Finally, let's see how to apply our technique for synthesizing programs with loops. For repeat loops, we can equivalently represent its semantic meaning by loop unrolling. So the same technique for synthesizing sequential programs still applies here. Then to deal with while loops, an important observation is that the semantic meaning of a while statement remains the same when we append it inside another if statement with the same condition and body. For example, the program while front is clear, put marker move is equivalent to if front is clear, put marker move followed with the same while statement. Inspired by this observation, we can adapt our technique of synthesizing if statements to synthesize a while loop. Every time when the model predicts a while condition, we know that only those input states that satisfy the condition will be relevant. Therefore, we still evaluate the condition, select the subset of the true branch, then we can generate the body of the while statement using this subset. So the synthesis of the while body terminates when the end of while token is generated, so that the model can continue generating the rest part of the program. And finally, the generation process terminates when the EOF token is predicted. So this execution-guided synthesis technique is the main technique we propose in this work. In addition, we also propose execution-guided ensemble for program synthesis. So ensemble method has been widely used in other domains of deep learning to improve the performance. And the high-level idea is that instead of just train one single model, we train multiple different models independently, so that at the test time, they may produce different predictions. Then the hope here is that if we can aggregate the predictions of different models in a smart way, then the prediction of this joint model will be better than simply relying on a single model. So such approaches have been very successful in domains such as computer vision and natural language processing, but its effectiveness hasn't been well studied for program synthesis. In this work, we make some adaptations of existing ensemble methods so that this is aware of the execution information. First, we can observe that for most deep learning tasks, it is very hard to tell whether the prediction is correct without knowing the ground truth. However, for program synthesis tasks, at least we can take a simple sanity test by checking whether the synthesized program is consistent with the input-output examples, and we can already filter out those predictions that are not consistent with the input-output pairs. Note that passing these input-output examples doesn't necessarily mean that the program can generalize to herd out test cases, but at least this is a very strong necessary condition. Then to ensemble the remaining predictions, we study several variants of ensemble methods, and we present the most effective two here. The first method always selects the shortest program, and it is kind of related to Occam's razor principle. It states that among all the solutions, usually the simplest solutions is the best. Then the second method selects the majority vote, so which means that it will returns the most frequently predicted program, and this aligns with existing ensemble methods. Then here are our results. We compare with the work from Barnum et al., which was the state-of-the-art on a Carroll benchmark at that time. And they use exactly the same framework we described before without applying our execution-guided synthesis and ensemble techniques. And we refer to their approach as MLE. So note that in the Carroll benchmark, each set of input-output pairs is annotated with a single ground truth program. But usually there could be multiple different programs that satisfy both the input-output examples and the herd-out test case. So we evaluate two metrics. One is exact match, which means that the prediction is exactly the same as the ground truth. Another is generalization, which means that we consider a prediction to be correct if the program gives the correct outputs on both the input-output examples and the herd-out test sample. We observe that each of our proposed techniques itself significantly boosts the performance over previous work, regardless of whether the model is trained with supervised learning or reinforcement learning. In particular, by combining both execution-guided synthesis and ensemble techniques, we improve the generalization accuracy from 77% to 92%. This is a 15% performance gain. Then in the next part of my talk, I will discuss my work on neuro-symbolic techniques for language understanding, where we show that our model can understand complex natural language passages and synthesize corresponding programs to answer the questions. Specifically, here I want to discuss the reading comprehension model. So reading comprehension has been widely studied by the NLP or natural language processing community. We are given a question and passage as the input. the model needs to provide the answer to the question grounded on the passage. As you can see from this example, the answers to most questions in standard reading comprehension benchmarks come from a single span in the passage. Therefore, the state-of-the-art reading comprehension models are designed to support single span extraction. Specifically, a language model such as BERT is used as the encoder to compute an embedding vector for each word token in a passage and question. Then there are some fully connected layers on top of the encoder to compute the probability of each passage token and see whether it could be a start or the end of the answer span. During the training time, the ground truth answer span is provided in the training set, which could be used as the training supervision. Although this overall framework looks pretty simple, such a model design works very well on standard benchmarks, and it even surpasses human performance on some data sets such as squad. Then if we take a look at these leaderboards, then we can kind of observe that the leaderboards of these benchmarks are occupied by approaches using powerful pre-trained language models, including all kinds of BERT. And in particular, you guys may also have heard about like the recent success of GPT-3 from OpenAI. They show that when we can have a very large amount of computational resources, we can train a giant pre-trained language model to solve various different types of tasks. This model could be extremely powerful when it is trained on abundant pre-trained data. And as you can see from this figure, this GPT-3 model could achieve decent performance, even if it is only fine-tuned on a few examples in the target dataset. Therefore, at this point, perhaps a common thought among people is that good pre-trained language models are all you need for NLP tasks. But is really the case? Recently, there was a dataset called JOB. This dataset was designed to emphasize discrete reasoning over paragraphs. As you can see, some categories of questions clearly cannot be answered by existing span extraction-based models. For example, arithmetic questions require the model to manipulate different numbers in a paragraph. Counting questions require the model to identify all related entities in the passage. And multi-span questions require the model to include more than one span in the answer. Compared with existing squad-style reading comprehension benchmarks, JOB dataset focuses more on numerical reasoning, and the formats of its answers are more diverse. Therefore, if we naively run BERT over this dataset, the F1 score is around 33, which is clearly below human performance. And even if we use a GPT-3 model, we could not see much performance gain. So the key message I want to convey here is that pre-trained language models are important, but it is not the only things we need. So to enable passage understanding with more advanced reasoning, we propose a neural symbolic reader framework. Specifically, our entire model have two key components. One is the reader component to encode the input passage and question, and another is the programmer component to produce the answer. So the reader component is roughly the same as standard reading comprehension models. Here we use a BERT model to compute embedding vectors for passage and question. But for the programmer module, instead of just using some fully connected layers to generate the final answer span, here our programmer module is an LSTM with attention. So this programmer will synthesize the program as a token sequence, so that after we execute the program, it will output the answer. And on the slides, I'm showing an example of the counting problems we discussed before. So this time, to solve these counting problems, our model will first identify some related passage spans in the passage, according to the question. Then we'll apply another count operator on top of these passage spans to see how many spans are related to the question. In this way, for this problem, our model could output the answer 2 because it finds 2 related passage spans. So notice that such programs are not provided in the data set, because usually we are only given the question and its ground truth answer, but we do not have any access to the intermediate steps to reach that answer. And it is also very common for other NLP or computer vision tasks. And I will discuss how to train our model without this program's data. So by designing our model, our approach combines the distributed representations of the passage and question generated by the reader component and the symbolic representations of the prediction rationale generated by the programmer component. Then there are two challenges related to our design. The first challenge is how to bypass the structured parsing process. So what do I mean by a structured parsing? So in general, for program synthesis tasks, usually we require the input to be in a structured format. For example, if you want to synthesize a SQL query, we need the input to the SQL as a database. So this should be a structured tabular data. It should have a well-defined schemas. But in our case, our program input will be the passage and question themselves, which are unstructured text. So we need to have some extra design so that our program could be directly executed on this unstructured data. The second related challenge is how to train our model with weak supervision, where no annotated ground truth program is available for training. Then to deal with the first challenge, here is where our domain-specific language comes in. The key design choice here is that we introduce span selection operators as some basic operators to select the arguments, so that other operators can be directly applied to the text by calling these operations as their arguments. Here we show some examples of how to use passage span and value operators to directly select arguments for counting and sorting problems. Then our next challenge is how to train our model with weak supervision without the access of the ground truth programs and only utilize the ground truth answers. There are two issues related to this challenge. The first issue is called spurious programs. So what does it mean? For example, if we take a look at this question and answer pair, if we ignore the question and we look at the possible programs that could generate this answer, then there are many different choices. It could be the answer 8 could be the sum of 3 and 5, could be the difference of 28 and 20. It could even be a counting program where it has 8 passage spans as its arguments. For humans, without looking at the passage, by looking at the question, we may kind of figure out which program should be the ground truth. Why? Because, for example, we see that the word total in the question, so it should be the sum. And we also see the first and last touchdowns, which means that it should be the sum of 2 numbers. So in this case, for humans, we can just judge which is the ground truth program according to the question itself. However, without human investigation, it is very hard for the model to figure this point out. Then the second issue is that the program search space could be exponentially large to provide a training supervision. So usually we need an exhaustive search of ground truth programs to start our training. And this may be easier for span selection problems, but it will be super hard for counting and sorting problems. For example, for counting problems, if we have the access to the ground truth answer, which is 2 here, then we only know that for this count operator, it needs to include 2 passage spans as its argument. But we know nothing about the spans to select, so we need to enumerate among all possible spans in the passage. Similarly, for like sorting problems, we only know that the key value pairs as the argument should include the ground truth answer, but we know nothing about other key value pairs to compare with. In this case, the search space of the programs grows exponentially to the length of the passage because we need to enumerate among all possible spans and key value pairs. And this is intractable given that our passage usually includes at least 200 words or so. Then to solve the spurious programs issue, we propose to train our model using hard EM with thresholding. Here, EM stands for expectation maximization. And I will not go into the technical details here, but the high-level idea of our algorithm is to train our model on like those problems with fewer spurious programs first, and then iteratively include those programs that the model is very confident about. So the intuition is even if we didn't explicitly design a curriculum to train our model could figure out which samples are easier questions in this way, and then it can progressively learn to solve more complicated tasks in the data set using our algorithm. Then we propose some data augmentation techniques based on the semantic meaning of these advanced operators, so that we can train our model from cold start. For example, we can manipulate existing span selection questions to generate samples to learn the counting operator. And we can use existing entity extraction tools to generate key value pairs so that it can make our initial program search space more tractable. Then after each training iteration, we can also use the current model to decode programs for training in later iterations so that it could really generate the programs for the real counting problems in the benchmark besides those synthetic ones. And also it could extract more key value pairs than what are supported in existing entity extraction tools. Then here are the results. We demonstrated our neural symbolic radar model achieves the state of the art at the time of submission on the job data set. So this work was published in iClear 2020 as a Spotlight. So it is the state of the art at that time. It outperforms other neural networks that are specifically designed for this benchmark. Now I want to show some predictions of our neural symbolic radar model on this data set. So we can observe that our model could better support the compositionality of different operators. And in particular, it naturally supports a multi-span prediction, which enables the model to perform substantially better than other models for this category. And here are some sample predictions of the sort counting and sorting problems. So we can see that our model is able to select the corresponding spans to these questions, even if we do not have any annotated ground truth programs for problems within these categories. Then we further evaluate our model on another benchmark called MathQA. Here, the questions require more in-depth mathematical computation. And as you can see, to solve these problems, it requires a wide range of math knowledge, including geometry, physics, profit gain, and probability. So we demonstrated without any change of the model architecture by simply adding more advanced mathematical operators into our language. Our neural symbolic radar model significantly outperforms the state of the art again, which suggests the flexibility and scalability of our design. Then to conclude my talk, in this presentation, we discuss deep learning for program synthesis or neural program synthesis approaches, where we combine deep neural networks and symbolic program representation for complex reasoning from the input specification. So we show that we can infer programs from very diverse specification formats, including input-output examples and natural language. Then to further improve the performance of program synthesis models, we need to effectively incorporate program semantic information, and this provides richer guidance for the synthesizer. And for example, we demonstrate that leveraging intermediate execution results and semantic characteristics of the program instructions is beneficial. Finally, I would like to thank my collaborators on these projects, including my collaborators at UC Berkeley, my advisor, Professor Dong Song, and also my other colleagues at Google Brain when I was an intern there. So thank you, and this is the end of my talk, and I would like to take questions.
Thank you so much, Xinyun. Sadly, we do not have time for questions today because we're on a schedule, but we really appreciate your talk, and I think this was really enlightening for all of us to learn.
Yeah, that's great. Yeah, thank you.
Thank you so much. Now we're going to have a quick, I think, 10-minute break before our next speaker, Dr. Philip Heller.